Third colligative property is osmosis. Osmosis is the flow of solvent from a solution of low concentration into a solution of high concentration. And the solutions are generally separated by a semi-permeable membrane. A semi-permeable membrane, let me see how I wrote this, allows solvent and small solute ions to penetrate. Well, I guess maybe a better word is to permeate, but let's just write to flow through it. But not large solute particles. Like proteins. Or starches, as we'll see. And what happens is if initially you have a solute particle on one side and only pure water on the other, so the water level will rise on the side of the part that has the solute particles in it due to the difference in the ability of the water molecules to get through because of the colligative properties, because of the solute particles making it harder to diffuse through. There is an osmotic pressure equation, and the osmotic pressure, let's define it. It is the amount of pressure needed to keep osmotic flow from taking place. The amount of pressure needed to keep osmotic flow from taking place. And there's an osmotic pressure equation, and instead of P for pressure, we use capital letter pi. And the osmotic pressure is directly proportional to the molarity, not molality, now we're back to molarity, of the solute particles. And here we have pi equals I times molarity times RT. We can think of molarity as moles per volume, moles per liter. And so really, this is just like PV equals nRT, where we've taken the pressure and put it on one side. This is really the molarity. So this is another version. These are versions of the ideal gas law. And of course, the one last thing we've had to add is the Van Hoff factor, because it's not just the molarity of the because the substances break up into more than one particle or can. And osmotic pressures can be big, and if you remember, we were talking about pressures in terms of millimeters of mercury. Now we're going to be talking about pressures in millimeters of water. So, and osmotic pressures can be big. Now, which of the following solutions will have the largest osmotic pressure? This time we have molarities, and they're all the same. So the only thing, well, let's see. So let's assume that M is the same, R and T are the same, so the only thing that's going to be different for these is going to be I. Here we have I equals 1, I equals 2, I equals 3, and I equals 4. So the last one will have the largest osmotic pressure. And this is the main example for osmotic pressure, for us anyway. There are many other osmotic pressures, and this is going to be a very long, a long example anyway, but hopefully it'll give you the idea of how to do this. It says, what is the molar mass of a protein if 5.87 milligrams per 10 milliliters causes a height difference in the solutions of 33.3 millimeters of solution at 25 degrees Celsius. The density of mercury is 13.6 grams per milliliter. And again, so this is osmosis. What we're saying is there's a height difference of the solution, and that height difference is 33.3 millimeters, or 3.33 centimeters. And this is 33.3 millimeters of solution, and like in past times, we will say that we will treat the solution as if it were water, because it has very similar properties. It's very dilute. Look at how many milligrams are in the solution. So, and I guess I should put a squiggly equal sign there. All right, so we know our mass of our protein. We know our volume, so we'll be able to get concentration, except that we don't know the molar mass. That's what we're looking for. So we've got a whole other page to work on this. So let's see, we got 5.87 milligrams per 10 milliliters, and it causes a height difference of 33.3 millimeters of water. And now we're going to plug into our osmotic pressure equation, and let's see, does it say, yep, 25 T is our temperature, 25 degrees Celsius, which is 298 Kelvin. For the osmotic pressure equation, we do need the 0.08206 liter atmospheres per mole Kelvin. All right, so let's write down our osmotic pressure equation. Let's see. Oh, and for our protein, I equals 1. That's the other thing we have to know. It is one big molecule. All right, so as far as determining our pressure, we know that it's 33.3 millimeters of water. And to figure that out, what we really need is we need to know how many millimeters of mercury it is. So we will use the density ratio. We know that the density of water is 1.00 gram per milliliter. We know that the density of mercury is 13.6. Oh, sorry, this is backwards. We know that gravity acts 13.6 times more on mercury. So in fact, the height of mercury will be much less. And we talked about that when we were talking about gases, how 760 millimeters of mercury would really be about 30 plus feet of water. So, and that this is based on how much gravity affects. That's how the density difference works. So 33.3 divided by 13.6, we get 2.45 millimeters of mercury, which we then need to convert into atmospheres if we're going to use R, divided by 760. 3.22 times 10 to the minus third atmospheres. So that's our osmotic pressure converted into the proper units. We know our I value. We don't know our molarity, and we can't because we don't know our molar mass. We know R and we know T, so we can solve this equation for our molarity. Let's see, pi over IRT. Yep. We have 1 for I. We know our R value. And we know our temperature. We can solve for our molarity. Let me do this on screen. 3.22 times 10 to the minus third divided by 1 divided by 0.08206 divided by 298. I get a molarity of 1.32 times 10 to the minus fourth. Molarity of protein. And so let's see, we know the molarity, we know the volume. Molarity is moles over liter. Take our volume, turn it into liters, we can get moles. So 10 milliliters is 0.010 liters. 1.32 times 10 to the minus fourth moles of protein per liter. So move the decimal point 2 more places, or change the exponent to minus 6. And we're almost there. We know our mass, we know our moles. We do have to convert milligrams to grams. And when we have grams divided by moles, grams of protein divided by moles of protein, we can solve for the molar mass. And proteins are big. 0.00587 divided by 1.32 exponent 6 minus. This one's not even that big. Still, it has a molar mass of 4.45. times 10 to the third grams per mole. And really, the examples you're likely to see on the homework and recitation are a little less involved than this typically. They involve plugging into the osmotic pressure equation to find out what the osmotic pressure would be.